Hello, thank you for this opportunity to present my work as part of the interview process for a position at IPNL Lyon with the ALICE collaboration. In this talk, I'll present a brief summary on various projects I worked on from my master's to my recent postdoc position. First, my master's project, where I helped in the design and the construction of a time projection chamber. This project was also continued well into my PhD. Here's a simplified picture of the motivation for building this TPC. This here is a representation of quark-gluon plasma. Every plasma, be it electromagnetic or strong nuclear, has an associated property called the Debye screening length. The Debye screening length is the radius of the sphere beyond which a particle within the sphere cannot feel the influence of strong nuclear force from particles outside of the sphere. So if a particle was present like this, let's say a heavy quark pair, it can only feel the presence of strong nuclear force by other quarks and gluons within the sphere. Now, if for this particular plasma, if the Debye screening length was smaller than the interparticle distance between a quark and anti-quark pair, then they cannot feel the effect of each other and they become disassociated or they become unbound and they kind of melt into the plasma as shown simplistically here. So this reduces the yield that we measure at the detector, and this is known as the suppression of heavy quarkonium in quark-gluon plasma. If I have a system like the epsilon state, where the 1s, 2s, and the 3s states have got different interparticle distances, and let's say that the Debye screening length of plasma is greater than the interparticle distance between 1s and 2s, but less than 3s, the 1s and 2s will continue feeling the effect of each other in the medium, whereas the 3s will kind of become disassociated in the medium and thus will melt. So we will observe a suppression in the 3s particle and no suppression in the 1s and 2s. To separately build and reconstruct these three masked states, we need a detector which has a mass resolution of 120 MeV, which in the S-Phoenix environment, in the collaboration of S-Phoenix, which is at Brookhaven National Lab, translates to a detector requirement of having a tracking resolution of 200 micrometer. For this, we built a time projection chamber. To build a TPC, the main bulk body of the TPC is the field cage, which provides the field lines for ionized charge to go towards an avalanche stage. To build this field cage, we need a workbench, which is called a mandrel. I participated in the first few years of this project. Me and the professor, Tom Hemmick, were the primary drivers of this project. So I completely participated in the designing and the construction of the outer and the inner mandrel. Including the outer mandrel was built as a 12-sided foam cylinder, which was then lathed into a perfect foam structure, 12-sided structure, which was then lathed into a perfect cylinder. Along this process, I was able to utilize my engineering degree from my undergrad, and I also got a certification as a machinist. The next, in electrical CAD, I designed the two field cages and supervised the manufacturing of these circuit cards. The insulating layer of this TPC was a solid layer of Kapton, which was wrapped up multiple times on the cylinder. This entire tension rod system, where the Kapton could be wrapped under constant tension, was the first big project that I contributed in this for this detector. Next came the designing of the gas electron multiplier and including the frames and choosing its different drift voltage and the field voltage between the different gem layers. For this, in this project, I supervised 3 bachelor students as part of their thesis work, and us collectively made the full design, and we got this manufactured at CERN. I also designed the zigzag pad plane in Eagle and using some back-end machine learning coding. I built 4 full modules. The overall TPC required 72 modules. These modules that I built were taken at test beam and were not utilized in the full detector. The full production and the full assembly of this detector, and with its recent installation in Brookhaven National Lab, was done after my years at Stony Brook, and thus I could not participate. But I'm very excited to see the detector that I participated a lot in its design to be installed, to be running and to be in operation and taking physics results. In parallel to all this, I also was instrumental in the full design and construction of a prototype TPC that we took to testing at Fermilab in 2018 and 2019. This prototype TPC was essential for us to finalize on the choice of gas, the drift field, and the effectiveness of running the gas electron multiplier in low ion backflow mode. At this test beam, we achieved a position resolution of 130 micrometer. Just a reminder that the position resolution that we wanted to achieve was 200 micrometer, which means we did way better than we expected to. For this entire work of 4 years that I was involved in this project, I got 2 awards in this process, one in 2016 and one in 2018. One technical paper is presently being written, and I also wrote 2 conference proceedings and gave 3 poster presentations at international conferences. The next project, which became my PhD thesis, is to study if quark-gluon plasma is created in small system collision. Specifically, I analyzed the deuterium-gold collision. Let me begin with a quick motivation. One of the cleanest probe that we know that a QGP is produced in a system is to study this ratio called the nuclear modification factor. This, in simple word, is a ratio of particle yield in AB collision divided by that in PP collision, where the AB can be gold-gold or deuteron-gold. For instance, this is a schematic of a gold-gold collision. Let's say in this particular impact parameter of collision, there were 60 individual proton-proton or proton-neutron or neutron-neutron collision. A particle yield in such a process, let's say yield of pi 0 in such a process, is that similar to that of the yield of pi 0 in 60 PP collision. Any difference in these two would then talk about how a gold-gold collision is different from that of just a scaled PP collision. In mediums where QGP is formed, when the RAA is less than 1, it's called a signature of the presence of QGP because the particle loses momentum in such a dense medium, and thus this ratio is suppressed and it's below 1. When we study such a suppression in D-gold collision, we notice that at minimum bias, it's equal to 1, suggesting that on an average, no QGP is formed. But it gets interesting when we bucket it in different centrality. What we mean by centrality is we're studying these processes in different average impact parameter of collision. When I use the term central collision, I mean collision which has a low impact parameter, which means the 2 nucleons were completely head-on. And peripheral collision is when the 2 nucleons just graze by one another, or in other words, have high impact parameter. It was realized that in central collision, we observed a small suppression at high PT corresponding to possible small QGP droplets being formed. Whereas in peripheral collision, we saw an enhancement which could not be explained by any known physics effect. Why would a peripheral deuteron-gold collision produce more pi zeros than that of a PP collision scaled appropriately? I speculated if the scaling that we do, when I use the word scaled appropriately, like the number 60 that we decided in this, is it possible that the way we determine that number is wrong? Because this number is not a purely experimental number. It takes some input from experimental data, but it's obtained using a theoretical model. Is it possible that this, which is very, very successful theoretical model in heavy ion collision, does not work for small system collision? So a novel analysis was introduced to circumvent the requirement of using this model. In this, we use direct photon, those that are created at the initial scattering of two nucleons is used as a proxy for number of binary collision. As direct photons do not interact with the medium, it becomes unaffected. And thus, if we can count these direct photons, they become a direct indication to how many direct binary collision took place in the interaction. This required a simultaneous measurement of pi 0, which is easy. You just look at the 2 photon signal, and a very challenging measurement of these direct photon. It's challenging because most of the calorimeter is cluttered by information from decay photons, and thus requiring just a direct photon, which is a less than 1% signal, is where most of the challenge is. This entire analysis chain from the calibration of detector to simulation of detector to understand detector efficiency and the ultimate obtaining the invariant yield was solely done by me. Once we have these direct photons, we use them to look at the number of binary collision, and we showed that in central collision, the number that we obtain from the theoretical model is equal to that we get from direct photon, whereas in peripheral collision, we're off by about 15%. And this is the reason we see an enhancement in peripheral collision. We went one step ahead and we used this number of binary collision from direct photon, put it into the equation for nuclear modification of pi 0, and looked at how it looks like as a function of number of binary collision. The peripheral collision enhancement completely disappeared, but the central collision suppression still remained. So here we show an unambiguous result where there's still a 20% suppression in central D-gold collision with a 4.5 sigma significance without having to have a caveat of but with etc. etc. This work is now currently under review. It's been submitted to PRL and it's currently under review. I also wrote 1 conference proceedings and gave 4 talks on this project. For this work, I was given the AGS BNL Thesis Award in 2022, and recently I've been nominated for the APS Thesis Award.